Thanks everybody for joining us today. We are very excited to be talking to this group about a new product, and really the first product of a new family of products from Micron Optics. And this is called the si255 Hyperion. For all of our presentations, we'd like to reflect on what it is we do and why we're in this business. And I think we share a mission with a lot of you, and that is to use cutting-edge optical technologies and invest our resources, our intellectual and emotional resources, to really enhance safety, security, and well-being of people, be it through civil structures, protecting the world's structures, enhancing comfort, enhancing safety. These are the things we do with our technologies, and it's something we're proud to be a part of, and we know you are as well. Today we're here to talk about the si255 Hyperion, and here's a picture of the unit. We're excited to introduce this today as bringing a host of new capabilities into the optical sensing world. It brings about the world's fastest and widest scanning laser, 160 nanometers at 1 kilohertz speeds. So these are ranges that were only available in the lab a few short years ago, and only at static speeds. Now we're able to bring this to market to enhance measurement capabilities over a large range of wavelengths at dynamic speeds. This unit supports the largest number of parallel channels. This is 16 parallel channels. No switching is involved, no degradation in speed or any other performance parameters as a result of multiplexing. This unit is also capable of something no other unit has been in the past, simultaneously making dynamic and what we regard as historically static or really absolute measurements of different types of sensors, FPGs, long period gratings, and others. While there's a lot new in this unit, what we carried forward was something that has been serving us and serving the community very well, and that's the Micron Optics swept wavelength source, which at this point in our history, we've logged over 100 million hours of field operation for this design. That's something that we're very proud of, and we want to continue, and that design at its core and in its spirit carries forward into the si255. The next few slides will highlight different characteristics of this instrument. This first slide, and there's a lot of information here, and I'll try to walk through some of these things at a reasonable pace. This instrument truly does simultaneous static and dynamic measurements. So if we look at all of these different measurement scenarios, and I'll highlight them in a moment, all of these are taken on the same instrument at the same time. This is based upon a high-power swept wavelength laser, which gives us the opportunity to look at not only a number of channels, but high-resolution features in sensors, as well as deep dynamic range features in sensors. So if we can, let's start with the image on the top left. Here we see a non-apodized grating, a uniform period FPG. And although this instrument is scanning at dynamic speeds, the laser is literally scanning at a kilohertz, you can see this response all the way down below -50 dBm, where you can see side modes and high-resolution side modes of this FPG. So very much like an SM125, the si255 shows you the actual spectral characteristics of your sensors. So that we think that's exciting. If you see the trace to the top right, there's a couple of very well apodized FPGs, and here you can see that the side modes have been suppressed by many tens of dB. If we were looking at this with a traditional dynamic instrument, be that an SM130 from Micron Optics, or if this were any other type of dynamic interrogation system, a diode array, an edge filter, or something like that, we would be limited in the receiver dynamic range to about 10 to 13 dB. This is the traditional limit of a linear receiver. So here we're seeing one of the great enhancements of the si255, and that is a new receiver technology that affords us the bandwidth at high speed to see high-resolution spectral features like in this non-apodized FPG, but also the speed and the gain over a larger dynamic range to detect at low optical power levels. So that carries us over to the middle left image. Here you can see a full spectrum taken on a single 1 kilohertz scan. So every time the laser scans, we capture a full spectrum like you would on an SM125, but 1,000 times faster and on 16 parallel channels. We combine the deep dynamic range of the receiver circuitry with this high speed, and you can see si255 can accommodate differential losses of greater than 20 dB on a single channel. So here we have some very high reflectivity gratings, and here we have some very low reflectivity gratings. And all of these sensors are seen with equal quality and have equal resolution and repeatability of the measurements without any user settings, no gains to change, no peak detection parameters to modify. Rather, the system captures the entire full spectrum and then runs some very stable and powerful and sophisticated peak finding algorithms inside of the unit, and we'll talk a little bit more on how that's accomplished. But this full spectrum trace in blue is converted instantaneously to these peak values that you see as red lines, and those peak values are streamed at speeds of a kilohertz, and that's what we see in this middle right graphic. So while we're taking full spectrum data like the 125, and while we're seeing many tens of dB dynamic range, we're also accurately and repeatedly streaming peak detected data at high speeds. And here you see just one of these sensors on this channel highlighted with a standard deviation of about a half a picometer. So exactly the type of precision and resolution that you're accustomed to seeing for micron optics instrumentation. Unlike dynamic systems before them, however, this is not just repeatability, but there is actually an onboard gas cell, just like in the static interrogators. As you can see, if we can profile in this instrument what a sensor grating might look like with high resolution, then we can also profile internally what a gas cell would look like. So on each and every 1 kilohertz scan, the si255 is referenced to an absolute traceable NIST gas cell. So this is also something very new in the industry, to take traceability, which has been relegated to static measurements, and bring that into the dynamic space. So now when you're making measurements and you require 100 or 200 or 5 or 1 kilohertz measurements, but you need to know absolutely that this strain is referenced over years, or this temperature is referenced to an absolute calibration standard, you have that capability within the si255. So these kilohertz internal peak detections can be used to look at things like accelerometers. On the bottom left, we see the Fourier transform of accelerometer products, and you can see a very strong 100 resonant mode and many orders of magnitude of signal to noise. And this is something that's brought about by the high repeatability, the clean measurements, and the fast rate of speed. So again, these measurements are performed simultaneously along with what look like a static measurement from an SI-125, all on the same instrument, all at the same time. The dynamic range is really available to each sensor individually. So there is no saturation of one sensor to the detriment of another. There's no increasing gain to be able to see small sensors to only the ability to see your strong sensors. It's a full dynamic range on each sensor. And there are, unlike other solutions where full dynamic range can be available, the user is not responsible for managing settings. They don't need to choose a particular gain for a particular channel or a particular sensor. Rather, detection capability is always available on all channels. No configuration required. And in the bottom right, this is a really interesting image, so interesting that I'll blow it up here for a minute. If we combine the low noise of the acquisition system with the high speed of the acquisition system, and then what's really new is the traceability of an absolute reference that guarantees that your system is not going to experience picometer drifts over time, we can use that information and some averaging to get to incredibly precise, high-resolution measurements that are enabling new types of sensors in many different markets. So here you can, with each division, there is 1/10 of a picometer. And this trace would carry on, not just for the 1 second of data shown here, but over periods of time. And you can see the standard deviation of this measurement is under 10 femtometers. So what this allows sensor developers and system integrators to do is really push the limits of what's possible in a sensor. How precise can the pressure transducer be? How much strain can you induce on a fiber? It's limited. It's a stiff material. That limits what sort of resolution you can get in an acceleration or in a pressure. But if you can reliably trust your interrogator to show changes in the femtometer region, then all of a sudden you can look back to the sensor and say, how stable can I get this sensor now that I know my interrogator's not drifting? So that's the simultaneous static and dynamic feature set of the si255.
So Todd, excuse me, just for the everybody online, this is Tom Graver speaking here, and I'm sitting next to Mike Baez watching some of the chat and comments and questions come in. And one thing is they're asking for clarification on, does this really do Fabry-Perot sensors, and how does it do that? So I'm not sure if this is the slide on which to do that or if you want to weave that in coming up.
Well, the answer is it sure does do Fabry-Perot sensors, and we do have a slide coming up to address that. So thank you very much for the question.
Yeah, keep those questions coming in. That'll help us tailor this to what you want to know.
And in fact, we utilize some Fabry-Perots on this very slide to demonstrate the huge sensor capacity the si255 has. We've mentioned 2 improvements in this platform, one being the 160 nanometer swept wavelength laser, and the other is the 16 parallel channels that are simultaneously captured. So to prepare this slide, we connected 16 different Fabry-Perot sensors to the 16 different channels, essentially loading over 200 peaks on every single channel. So what we're showing here is a table of over 4,000 peaks which are being captured, detected, and transmitted at a kilohertz. So this represents, I think, a new record in terms of sensors per second that can be captured, or rates of sensor measurement. But more importantly, rather than just setting records, it enables customers to fully instrument their structures, to not be limited in the types of sensors or the locations where they'd like to put them, to fully understand the behavior of whatever structure that needs to be measured. Historically, in trying to get full coverage on, let's say, a bridge, for example, system integrators have been obligated to either buy 2 interrogators or sometimes go with a dynamic interrogator with 160 nanometer wavelength range, which was greatly enabling, except when it comes time to physically connect all of the sensors and manage the real system losses, that 10 to 13 dB, we understand and appreciate, can be very limiting. So if we enhance that by another order of magnitude, and we're greater than 20 dB in our loss budget, we really see the ability to measure many, many hundreds and even into thousands of sensors at dynamic speeds. So how are we doing 160 nanometers? It's really the core of our technology. It's advancements in the Fabry-Perot technology, as well as in our partners and other optical components. There's a graphic on the bottom left there that shows in black and in yellow a couple of different ASE source designs. So these would be traditional erbium sources, which are great sources, very high power, very nice flat low noise sources. But as you can see, for normalized to about a 0.1 nanometer resolution, and a reasonably cost-effective, commercially available ASE source would peak out, somewhere between -10 and -5 dB per tenth of a nanometer, which is approximately the density that you'd receive from a sensor FPG. If you look at the same trace with our Hyperion laser, you can see we're about 12 dB or 16 times higher on the individual output power, which allows us to share power over 16 channels while maintaining good loss budget, good reach, good dynamic range. Additionally, the width is about 4 times that of the ASE. So instead of 40 nanometers, it's 160 nanometers. So there you see a 16 times increase in sensor capacity times another 4 times from the spectrum range. So that's really how we get to this very large sensor. So let's talk a little bit about the different things that can be measured. Hyperion has been designed, the si255 Hyperion has been designed with flexibility in mind. Our history and many of our partners and customers' history has been in fiber grading measurements, and they continue to serve the market very well and will do so increasingly in the future. But we recognize and understand and have learned from our customers that other sensor types are emerging as being critically important. And so with that in mind, we've designed many of the features of the si255 to be flexible with regard to the types of sensors we measure. Peaks or valleys can be equally measured with the same sort of resolution and accuracy. Narrow features or wide features. For our users of the SM130, some of you may know that when you change the bandwidth of the FPG, there are implications with regard to the specifications, so the performance. No longer the case with the si255. We can look at FPG, Fabry-Perot, long period grading, long gauge interferometer sensors. Spectra that's uniform or apodized can be handled equally well. High or low reflectivity can be accommodated by that per sensor dynamic range. And really, the ability to independently and individually detect these different types of sensors is built right into the core of this instrument. So if we start here in the center left, you'll note that for this apodized FPG and non-apodized FPG, the spectrum is very, very different, but the result is very similar. Our ability to find those peaks reliably and repeatedly and accurately are baked right into the detection algorithms. On the top left, you'll see a spectrum of one of our new family of Fabry-Perot sensors. And this Fabry-Perot sensor is designed in such a way that we have reflection nulls within a given bandpass. And we use that bandpass to multiplex multiple Fabry-Perots in the spectral domain. But here you can see we've selected peak detection parameters from among a list of pre-qualified calibration or detection. We can choose FPGs, we can choose Fabry-Perots. Here we've chosen about null Fabry-Perot, and you can see the result of this Fabry-Perot accelerometer trace as that spectrum changes. And the Hyperion unit detects those nulls and plots those as a function of wavelength. Here in the middle right, you can see a different type of Fabry-Perot sensor with varying degrees of contrast, and the si255's ability to resolve those peaks and those valleys and those nulls. We have customers using sensors of this variety, really taking advantage of the full spectrum detection capability of the unit for Fabry-Perots, while simultaneously some of the internal peak detection for higher speed. So again, no gain management, but we do have selectable parameters. You don't have to invent your own parameters. We have some that we've built, and we're qualifying and creating some for the results. The detection is facilitated in this way. We sweep a laser and we digitize the entire spectrum of all 16 channels, just like you would with an SM125. But this isn't transferred at those very high rates of speed over to a user computer. There's really no bus or no communication protocol that would allow this at those rates. But rather inside of the hardware of the si255, we make an evaluation of the spectral shape during the laser sweep. And we do some inline real-time digital filtering. And then we have different detection algorithms to find what those peaks and nulls are. And so with that process, we can look at different types of sensors, and we can also bring to the user the capability to choose among the pre-qualified peak detection presets, or even edit and create their own types of presets. And here's an example of one that I created on the bottom. If you look at this, this plot on the bottom left, this is 3 FPG sensors, all of apodized FPG spectra. But the sensor on the right, we can clearly see there's some peak distortion. Now, why might this be? This could be a sensor that was deployed in the field, perhaps in some sort of a subsea application, and there was an unexpected transverse strain on the sensor. Or perhaps it was in a monitoring hoop strains in some sort of a containment vessel, and there was a tremendous change in temperature that imparted really an unavoidable transverse strain. Using older technology, you can see that it would detect 2 peaks. And our ability to use that information or calibrate that information is compromised as we have to manage a changing number of peaks. Perhaps another scenario would be this is a high quality FPG sensor that's been stretched to 3 or 5% strain, and it's moved 30,000 picometers. That information is extremely valuable. We want to know if it's moved 10,000, 20,000, 30,000 picometers, but perhaps the precision of 1 picometer is of less import at that point than is knowing within 10 picometers exactly where that sensor is and that we reliably detect that 1 peak. So you can see by using the programmable real-time digital filtering, I can change the way the instrument perceives that FPG. So I can effectively change the resolution of the instrument on this one particular channel, leaving the rest of my channels at a high precision, high resolution like we might have for this Fabry Pro sensor. But on this channel, I'll change it and increase the digital filtering and really resolve that as just one robust peak that I can detect over a wide variety of conditions. So those are a couple of examples of the flexibility of the si255. We mentioned earlier about the gas cell that's on board, and the one thing that we know that having a gas cell on board brings our customers is certainty about the measurement. So certainty about the But what we've really discovered is in mission-critical applications, and we've been taught this by our customers, as telling them that we've corrected the wavelength with the gas cell is communicating to them that we are sure that the instrument is functioning properly before we ever pass any wavelength to them. And that's what you can do with an onboard gas cell, and that's what you can do in a dynamic system now with the si255. So if we look at the bottom left, many of you will recognize this spectral trace. This is an internationally recognized certification standard for wavelength. This is a hydrogen cyanide atomic absorption cell, and it's certified by European standards bodies and American standards bodies and Asian standards bodies as having very specific and precise lines. If you illuminate this cell with particular wavelengths, you will get absorption at frequencies no matter the temperature or other environmental conditions. Since we have one of those cells on board inside of the instrument, then we can check during operation and pass the information on to our users in mission-critical applications that all systems are go within the interrogator prior to ever considering taking action on a reported wavelength. So this is akin to really having what's called the two-man rule in certain military applications. We're going to take an action that is going to have significant implications, be that militarily or otherwise. We want to get an affirmation from 2 reliable sources that we agree on this outcome. This standards body published gas cell trace is one of these sources, and the internally measured trace of the gas cell is another source. So what can we capture with this gas cell trace? Well, if somehow incorrect calibration information were loaded, then there would be a shift in this gas cell spectrum. There would also be a shift in the measured sensors. If we overlay our measured gas cell spectrum to the published, they won't line up. In other words, the key won't fit the lock. Our measurement being the key and the published standard being the lock. If there's a failure in the gas cell, its spectrum will be different and the key won't fit. If there are fiber breaks inside the instrument, if there are data acquisition errors, if there are power conditioning errors which lead to an abundance of noise in the system, all of those things can be captured as instrument health issues, and that data never delivered. So for the applications where customers simply cannot afford to have incorrect data passed, this instrument can be self-aware and block any transmission of data if these conditions haven't been met. So that gives you certainty in the instrument. What's also important to any sensing application is certainty about the sensor. So we've talked a lot already about the simultaneous full spectrum and peak detection capability, and that's really great for setting up sensors and ensuring that splices are low loss and that bend radiuses are managed. But even after the initial installation, this full spectrum measurement value to the user in terms of the certainty of the quality of his sensors. So let's look at the top right. Here we see two peak detected values which would be streaming into the applications at a static data delivery rate of 10 hertz. The user will be able to view and monitor these blue traces. This is the source of the spectrum that goes in. We, the user, know something about our application. Is this spectrum acceptable? Does this mean a good sensor on the left and a bad sensor on the right? Well, from our perspective, certainly we don't know, but we can pass that information to you, the system integrator that does understand the meaning and whether or not this is a sensor that should be used. Turn the pitch of the wind turbine blade, or to offer information to the steel mill operator. All of these things are critical decisions that need to be based on only the best quality information. On the top left, we can see a comparison of two different dynamic interrogator technologies. In both cases, we're looking at FPGs, top FPG and bottom FPG, in two different strain states, a blue strain state and a red strain state. If I look at the two left plots that were taken from a different technology, high-speed interrogator, and I look at the spectrum, and I ask myself, are these sensors healthy? Are these sensors still bonded in the way that I can trust? I would have to look at this and say, perhaps there's not enough information to make that assessment. If I look at those same two sensors in the same two conditions with a Hyperion unit, also streaming data at kilohertz rates, but capturing a very high spectral, high resolution trace of those sensors, I can definitively say, yes, this sensor on the bottom is seeing a linear translation of its overall spectral response. I know that to be a well-bonded and healthy sensor. When I look at the one on top, I can say, I'm beginning to see higher order mode structure. I may consider this to be in danger of delamination. So I want to know for sure that my instrument is functioning to exact standards, and I want to know for sure that my sensors are performing in the way that I need them to. And the si255 Hyperion can bring you certainty in both of those regards. So where are we today? Well, the si255 has been officially publicly announced, and this is part of that process. Available today is the most capable incarnation that we can envision of this unit. It's the full 160 nanometers. It's the full 16 channel. It has the gas cell. It has all the dynamic range. It has all the feature sets I just talked about. And these are already realizing incredible applications we started with the most difficult so that we could then bring about different combinations of this technology. And what you'll see over time is Micron Optics product portfolio and our rollout of new products will proceed at a pace that you haven't seen in the past few years. We've invested quite a bit of time and energy to bring this about, and we're super excited that it's a reality. And from this point forward, we're going to see things that address specific OEM opportunities, as you see on the top right, but really different configurations and combinations of these product capabilities to offer the right products at different price points and different feature sets in the market. So today we have the si255, and that means 16 channels, 160 nanometers. Coming soon, we'll 4-channel generally available instrument configurations. This will offer a smaller footprint and a lower price point for entry into this technology. Even today, we're shipping OEM versions of this technology. Some of these feature sets were developed to solve particular solutions. And you'll see in a coming slide that really what the si255 and Hyperion can do is not contained in this large rack-mountable enclosure, but it's contained in a very small set of optics in small form factor OEM configurations that can tie directly into specific solutions. So that's another way of saying what you may have seen from Micron Optics in the past that had transmitter cards and receiver cards and data collection cards and data processing cards. all of the functionality we described is happening not only in hardware, but in a single piece of hardware, in a single PCB. That allows us to design the unit in such a way as to operate without a fan over a much wider operating temperature range of -20 to 60 degrees. The core of this technology is currently under tech certification, and we'll soon be able to bring that certification and that assurance to users of this in all configurations, be it 16-channel OEM. As of today, we have full support for a TP API with complete API in LabVIEW, Python, C++, MATLAB, working on C# and others, as well as a group of specific simple examples that can be used to build applications in each of these languages. This product was developed initially, as I said, with solving partners. And what we are doing to enable those partners is really developing and distributing a more supported and well-developed series of APIs than you've seen from Micron Optics in the past. So we really want to engage those developers to bring this technology into broad spread use into systems for which we know we're a small part, and we think the API is a good for systems. But we also recognize that Nlight has been a good tool for many of our users, and so Nlight support for this instrument. So here's a feature that to come out, and again, this is a solution to a particular problem that just plugged in so nicely into the Hyperion platform that is something that we feel like we really want to make broadly available. And that is Micron Optics has been able to develop an unpolarized source that takes advantage of all of the rest of the capabilities we just described in Hyperion, but eliminates any offense on the sensor. We know that many times sensors can be treated in such a way that birefringence isn't an issue. But when it comes time for specific implementations, be they embedded in composites or designed into medical devices, the physical constraints are such that the fiber may just experience transverse strains, but they still bring incredible value to users in the strain measurements they can make. And so for that reason, we've really put a good bit of energy into understanding how to create a source that doesn't bring with it the trade-offs of traditional broad spectrum sources, but leverages the strengths of a laser without the penalty of polarization. And we've done that and deployed it on the Hyperion platform. So this is a different source option. It's not the 160 nanometer source, but it carries with it very high power, like a laser, but non-polarized output, like an ASE source. So with those two features, you maintain the full accuracy, 1 picometer, the full speed of a kilohertz, the full dynamic range of these many tens of dB of loss budget, the same high-resolution line width that allows us to look at detailed spectrum, and the same sampling resolution, 20,000 data points over spectrum. And because it's high power, we maintain the ability to have 16 parallel channels. So what is the trade-off? Rather than being 160 nanometers, it's a 40 nanometer source. But again, because it's high power, you can multiply that 40 nanometers times 16 on the Hyperion platform, on the si255, and still maintain upwards of 1,000 sensors across that range at dynamic speeds. So we see a couple of screenshots here of a 40 nanometer range, and again, you can still see the deep dynamic range, the high repeatability, and the multiplexing, the peak detection, the simultaneous static and dynamic measurements. So this is a development we're really excited about and is being very well received in the market. We know that there's a need and there's been a desire to have an instrument that brings all this capability with a polarization insensitive optical property. So how is all this possible? What are we doing? And our core technology will continue to reside in the tunable filters and the tunable lasers, but the vast majority of our hardest efforts in the past few years have gone into the electronics, the hardware, and the software. And really, this is an FPGA-driven platform. So we're taking advantage of the latest generations of programmable hardware and very high-speed data acquisition hardware to capture a tremendous amount of data and in real time process, store, and control hardware with that FPGA inside of a compact design. So there's as much as about a gigasample per second of data flowing through this FPGA when you look at the 16 channels at 20,000 samples at the kilohertz speeds. But the hardware itself does all of the data acquisition, all of the conversions from spectrum to peaks, all of the conversions from peaks into wavelengths, and then all of the control of the laser, all of that happening in a single chip that is programmable. That also means that the measurements, unlike any previous generation of certainly Micron Optics optical interrogator, are deterministic and they're real time. As the laser is sweeping, it's making determinations about what the wavelength of that sensor was before the laser ever makes it to the next sensor. That makes it possible to bring the Hyperion instrument into the OEM control loop. As sensor information is being read, the wavelengths are being generated. So you can envision, perhaps in a wind turbine blade application or other control system applications where real-time control and zero latency are important, this platform plugs in extremely well, and it is really a perfect match. So the si255 is the first offering from this platform, but there are many more incarnations to come. We've spoken already about different optical source types. We are looking into and have begun developments of different receiver types and really different core technologies. The platform itself is really agnostic. It's exceptional at gathering an immense amount of data, real time in distributing that data, and whether it's a source, a diode array, receiver, a different type of tunable laser, all of those compatible with this platform. si255 is the first. There will be many more to come. So what does this mean with regard to the other instrument software that are being used? Very simple answer. Micron will continue to support the X25 and X30 models. We appreciate all the work that's gone into getting these instruments designed into critical applications and are committed to continue supplying those instruments and to continue serving those applications. And we will certainly work with customers to communicate what we know about Hyperion's capabilities as they are today and as they will develop. And we'll work with the customers to migrate over to this new Hyperion platform as it makes sense for their programs and their applications. So these will live together in harmony for some time. Clearly there are things that Hyperion can do that the X25 and X30 can't do. And we believe over time that many customers will choose to migrate, but that migration will be based upon what's good for the customer. So,
Todd, I'm going to interrupt you here for a second. We have a lot of good questions coming in, and I think maybe let's weave them in at this point, and
okay.
then the next slide you gave us a glimpse of there we can come to in a moment. I think the questions really speak to the caliber of the folks on the call this morning. Very insightful questions. One is about ruggedness of this design.
Yeah.
Putting this thing out in the field. How does this compare with previous designs that have been in field applications with our SM130s and 125s? What have you done in this design to improve and
okay, great question. To first order, the optical core of this interrogator, as I mentioned early on in this presentation, is an evolutionary design from that swept wavelength laser based upon our tunable filter, which has been in the field operating for an aggregate 100 million hours. And so when we look at our that have resulted in stoppage of operation, we can say unequivocally it's not been the laser. The laser really continues to function over time. Where we have seen some areas for improvement in durability and quality has been in the overall instrument architecture itself. I mentioned a little bit earlier about there being 5 different boards in the SM125 or the SM130. And frankly, where we've seen the vast majority of our field failures have come in board-to-board connectors. These are power distribution cables or signaling cables, things that can that can be susceptible to shock and vibration over time. So what we've done in this instrument is design all of those out. The electronics, the data processing, the data capture is all within a single PCB design. All routing of electrical signals, be they signal or power, is happening within this sandwich multi-layer board. So intrinsically, that's going to lead us to a more reliable, mechanically more reliable solution. Another advancement that typically we'll consider this sort of an internal improvement and not share outwardly, but I think it's relevant to your question, is the way we've architected the internals and how that affects both manufacture and ultimately long-term reliability. For an SM130, for example, we would manufacture a transmitter, manufacture a 4-channel receiver, bring together a data collection card and a single board computer, and at that point in time we'd be able to evaluate the overall behavior of this instrument. For the si255, we're taking a far more modular approach, and that is every subsystem in the interrogation system can be independently manufactured and independently certified. What that allows us to do is do much more of a batch manufacturing and batch certification process so that we can get a much greater degree of refinement of those quality systems in our processes. So specifically, when we build the boards will have a custom FPGA deployment that allows it to test every piece of electronics on the board before it ever sees any optics. When we build a laser, we will have a similar laser cassette that goes on all of our Hyperion units, and those will be independently qualified. And be it a 4-channel, an 8-channel, or a 16-channel unit, we are building passive optical cassettes in 4-channel blocks that if you build a 4-channel unit, you use 1 block. If you build a 16-channel unit, you use 4 different optical blocks, but they're all identical, which allows us to process these in a larger volume and really invest in the certification and the in-process quality checks that we'll be able to apply to these, such that when these cassettes come together, they will have seen many layers of qualification prior even to initial assembly. So we think that basing on the optical core, which has proven itself reliable, addressing those issues that we know to have been problematic in terms of power distribution by a single board design, and then really refining the manufacturing and certification process, is only going to see an increase in robustness over time. And incidentally, it's these same design changes that have allowed us to increase the operating temperature range. By having the single board design, all of our heat generating components are placed on the same side and directly conductively cooled through a heat sink. And so what that does is it puts all of our heat generating components in a very controlled environment that can only extend the life of those components and lead to long-term reliability in the field.
That's a good answer. I'm not sure we can survive that good of an answer on each of these questions, because we're down to our last 10 minutes here.
Okay.
But, I guess everybody can tell Todd's enthusiasm for what we've created here and what his team has done. Okay, so that's all really good. I was pulling up as you were talking, Todd, the July shock and vibe report. Where we've really run this thing through the ringer in 15G operating shocks and 25G non-operating shocks. It's a very rugged device and a nice improvement over previous generations. And I think if you look across the field of what's available there, I don't know that anything comes close.
And it's a good point. For this generation, we've enhanced the shock and vibe test regimen and specifications, so it will be certified to higher degrees than any of our previous instrumentation.
Okay, so moving on to other questions and jumping around a little bit on topic. Back to the operation outside the box and how the measurement is made. We're sweeping a laser, so this time of flight and speed of light correction needs to be taken into account.
Mm-hmm.
How do we do that? How do we understand the distance to the sensor and correct for that time of flight?
So the short answer is that we will be handling that in a very similar way that we've done the SM130, which is by knowing the distance. That distance is really an optical path length. We had a physical distance or distance that's it's really the time of flight that is of concern, and so by knowing what that time of flight is, by knowing the refractive index paired with the physical distance of fiber, we can take that measure into account when we calculate the wavelength. So what we've shown with this type of technology in the past and is to be implemented on this platform as well, by knowing that time of flight, bringing that information into the initial calculation, we take that into account when we do our onboard calibrations, so offsets can be completely compensated for and really return those measurements, be they at 1 meter or 10,000 meters, to within accuracies.
And I think the strongest point in that question was, is this correction automatic?
So as of today, the correction is not automatic, but within our planned series, absolutely. What's also interesting, and something I haven't explicitly mentioned, is that we are able, in the laser, at different. This is not something that is necessarily a feature that would enhance a user mode, but what we can do with that is by scanning at a kilohertz and seeing the effects of time of flight, and scanning the laser at 10 hertz and doing the same identical data acquisition, collection, and processing, we can see a differential in the time of flight effects on those sensors. So from those two measurements, very much like a wavelength-specific OTDR, determine exactly where those fibers are, calculate their optical path length offsets, and incorporate them directly into the compensation. So over the long, you see this to be a very seamlessly integrated feature.
Great. Looking here, I think you really have covered a few of these things. These questions came in, and then the slides came up on the topic. So in terms of continued support for SM125s and SM130s, I think it's clear there are years to come on us being able to deliver those on our support of those instruments. I think you in a few places throughout reiterated the point about being able to do Fabry-Pro sensors and FPGs all together in the same sensor networks, and then having some parameters that you can adjust to optimize for the types of sensors you have there. There's a question about draw tower gratings. Can I use draw tower gratings and higher reflectivity gratings all together? Different bandwidths and
absolutely. And I think we saw a couple graphics. I'll back the slides up. Well, to first particular graphic, and you can see with this high-powered non-polarized source, we're still seeing many tens of dB of dynamic range in the draw tower gratings. And if we look at this graphic, we can see a combination of strip and recoat, high reflectivity gratings, and draw tower gratings simultaneously being measured on the same fiber.
Very well. Let's see. Another question is, the insight here is right on the money. 16 channels of full spectrum is a lot of data. How do you deliver that at a kilohertz? So
right,
and across TCP/IP. So I think there's a little clarification is needed there.
Sure. This instrument was designed first and foremost as a dynamic interrogator. So focus has been placed on how do we deliver many thousands of sensors at kilohertz speeds, and how do we detect those sensors. We've talked to that at length. So at kilohertz speeds, we'll be streaming out all 16 channels of data at full speed. The full spectrum data, 20,000 data points per channel, is a lot of additional data to supply as well. So we envision the full spectrum data from this platform being used in one of two ways. When you're using it principally as a dynamic measurement interrogator, then being able to, at a lower rate of speed, say 10 hertz, view a particular channel for setup, diagnostic, assuring peak detection parameters are available. That data will be delivered at a low rate on a selectable channel at 10 hertz. So when you're scanning at a kilohertz, this is a kilohertz interrogator with spectrum, user selectable. We are also envisioning another usage mode whereby the user would not be interested in kilohertz full spectrum data, but is very interested in 16-channel, 10 hertz full spectrum data. And so that would be our second usage mode, where the TCP pipe would then be prioritized for receiving all 16 channels at full resolution at 10 hertz.
Okay, so you said something about we were envisioning. So just for the folks on the line, and as Mike pointed out, they're a varied group here. We are making a couple of sets of decisions here. One is what to deliver in the general purpose versions like the SI255. But the capabilities are all there. I mean, these things that you're talking about are not dreams, right? They're things that you've seen and demonstrated in the lab. It's just how we provision that
Right.
in different cases. So in an OEM case where perhaps somebody needed high-speed, full spectrum,
yes,
we'd look at ways to get to that.
Thank you. So the two data delivery modes I just described, 16 channels, kilohertz simultaneously, plus 10 hertz user selectable, that is a 255 data delivery mode. The 16 channels, 10 hertz, parallel full spectrum without kilohertz data will also be an si255 data delivery mode. What we are seeing is in certain applications and for OEMs where they would like to receive 1 kilohertz full spectrum data on 1, 2, or 3 channels. Clearly Ethernet is not the right avenue for that data delivery mode, but a high-speed direct digital interface is. And so when we go back to our OEM implementations of this unit and we look at the OEM available today, the way this data can be delivered is scanned, wavelength calibrated, and dumping all 20,000 data points directly into another FPGA for that OEM to process. Important, and we make the right solution.
Great. So we're right at the end of our promised time here, and it's I think it is appropriate to wrap it up here. I do appreciate everyone joining the call today and sending your questions as we went through. There were a few we did not get to, but I guess in summary here, what we've tried to accomplish, and I think we've done a nice job of it through Hyperion, is to address the many questions that have come to us in the days of the SM125s and SM130s. So how do we get more sensor capacity with greater dynamic range at higher speeds, and tying all that back into mistraceable absolute accuracies. All of these capabilities now are really contained in this Hyperion platform, and the si255 is just the first way in which we're delivering that and making that available to you. We're looking forward to our follow-ups conversations with you all right after this session, and to hear a little bit more from you about your reactions to what you've heard today and how this information lays against the needs that you perceive going forward. The bottom line is that this platform with you.
Great. For joining, we look forward to